Yeah, I'll
Okay,
just
so
Mhm.
okay, so
Yeah, I'll just share my
okay,
screen.
so yes, well, so let's start. Hello everyone to the third training session in MEMS. In this case, the speaker is Mr. Suman Acharya. I hope I said it correctly.
Yeah,
And okay, the topic today it's about MEMS simulation and modeling, and also sensors and actuators in MEMS. So please, Suman, the floor is yours.
yeah. Thank you, Carlos. I'm Suman Acharya. I'm a master's by research student here at International Institute. I'm working on surface acoustic wave-based gas sensors under Dr. Veda. So I like to thank IEEE Sensor Council group to for providing this opportunity. Today, I'll I will like mostly talking about different MEMS modeling and also like simulation, how to like perform the basic simulation in COMSOL, as well as I'll also like try to run some MATLAB code where I'll be doing few finite element analysis of a thermal actuator. So first, so I like to talk mostly about like I'll just model in COMSOL multiphysics and do the simulation. So how I have like divided this seminar is like first I'll talk about structure. I'll do some analysis on structure, that will be structure and analysis. So I'll also like do few example on eigenfrequency analysis where most of the like student are working on accelerometer gyro where frequency analysis like plays a vital role. Then if you have time, I'll also like do some time dependent analysis as well, and electrostatics, and also like electromechanical coupling, like how your geometry is like displacing, or how it is like there is a deformation on a like parallel plate actuation, something like that. So at last, like I'll talk about electrothermal actuators, and I'll also like run the MATLAB beam code, which is like designed by Professor G.K. Suresh. So I'll talk about thermal actuators. There, I'll be running different simulation on different designs of thermal actuators as well as accelerometers. So I was a like part of IEEE back in 2019, where I got an opportunity to design a thermal actuator. Pointer. Yeah. So at the time, this is the design which I had designed under the guidance of Veda. So there are other group as well that time who works on different sensors. So this is a accelerometer. This is thermal actuator, again thermal actuator. So this was designed by various students from different colleges. So at the time I didn't know about like any like sensors, accelerometer, or any like thermal actuators, how it works. But this platform gave me a very good opportunity to know like about the sensors, though I'm from mechanical engineering background. So the IEEE helped me to like model all of this thing and know about like different sensors. So I feel that this opportunity is a like very wonderful for the students who are in undergrad, or who is new to sensors. So if you see this image, oh, is this playing? Okay, yeah. So this is one of the design of thermal actuators. So if you see here, it's like when you like supply give a voltage, it is moving. Can point. Okay. So after that, like if you like keep on giving more voltage, at last it like breaks. So this device fails. So this is the design which I worked that type, and I have few of the videos here which I like quickly show you. And this is the another design. If you see here, it's moving. Just like the see. So we'll be like talking about various designs on thermal actuators or accelerometer or gyroscope, like according to the interest of the student, and I'll be helping to do the simulation as well as like modeling on that. So now I like to give a like brief introduction on COMSOL. I'll just open it, and I'll like teach you how to like perform various analysis in COMSOL. Uh, takes some time to open. So I like teach the basic COMSOL simulation, how to make geometry, how to give different boundary condition and all. So when you open the COMSOL multiphysics softwares, it's a multiphysics software. You can do various kind of simulation. This is how it looks when you open it. So if you just go to, if you let's say you want to like perform a simulation of a simple cantilever beam. I mean, I'll just make it here. Slide. So let's say if you like make a cantilever beam where you are it here. Yeah. So this is my fixed one. Like what will happen in cantilever beam is one side is fixed, and you'll be like giving a load in another side, right? Here, somewhere here. So I'll be like doing a simple COMSOL simulation like this. And if you have any questions, you can like ask anytime. So when you go to the new, like first you when you go to the file and new, so this is how it looks like. You go to the model wizard. So here you can perform you can work on various geometries like 3D, 2D axisymmetry, or 2D or 1D as well. So if you want to do a simulation much quicker in a very less time, you just perform 2D. So and otherwise, like you can always go with 3D, like how it exactly like behaves. So I'll be like I'll do one example of 3D, then we'll move to 2D as well. So if I click on 3D, here you'll be like getting a different physics. So you have to like select what what exactly you are performing. So since we are like working on cantilever, where I'll be applying a force here, and another side is fixed, it is a structural analysis, right? So I'll go to the, if you see here, you can go to see structural mechanics. If you so you can see different physics here. Otherwise, if you like not sure where exactly it lies, you can just simply search. So see like now you can search it as well. So solid mechanics will come. So if you double click on it and study, then here are like different like studies. What exactly do you want to like perform? Which simulation do you want to like perform? Do you want to like perform eigen frequency or frequency domain, stationary or time dependent? And there are also like various studies which you can perform. So like first I'll be like doing a stationary simulation. So just click on stationary and click on done. So after that, you will go to the main like uh, window, like where you will be like making a geometry, and you have like select solid mechanics. Under that, you can see various options here, and study, you are doing a stationary study. So first, what is the like first step in order to like perform any simulations? We have to like make a geometry, right? So what I'll do is I'll try to like make this cantilever beam here. And so, and here, when you go in the like component, you'll find everything here. If you go to the geometry, here you have to like select the unit. So you can just select it, either you want to work in scale, or micro scale, or meter scale. So you don't need to worry about this. You can simply change here, like if you like look on other FEA softwares like uh, Abacus or ANSYS, there what you have to do is you have to like, if you like select your geometry in micro scale, you have to like put all the other details such as material properties also in that scale. You have to change everything. But here you don't need to worry about, like COMSOL will take care of that. So I want to like, since we are like working on MEMS, it is like stand for micro electromechanical system. I want to like make my geometry in micro scale. So in order to make a geometry, you have to like right click on geometry. And since we just want, we are like working on cantilever, you can just go to block. You can click on block, and how much like give the value of width, uh, depth, and height. So here how it looks like. So your geometry will come here if I just click here. So this is the geometry which you have made. So if you want to change your width, let's say I want longer beam, let's say 100. It will like simply come like this. Yeah. If you want to change width, you can put the value, and this will change. So if you want to zoom, you can zoom it from here as well. And like left click on the zoom box, and just drag and hold. You will be able to zoom. So this is my geometry. So there are like various ways of making it. You can, if you want to make a cylinder or cone, or if you want to make a point on the surface of this one, or the any other like design, you can do that as well. And after that, if you go to the block, so you can see the position, which is like, if you are like take it is just the axis, like reference point from where it is being created. So if you like press this one and go to the center, it will be like designed from like your reference point will be at 0, like starting point. So this is how it looks like. So let's say you want to make a, like you can also make the geometry in other ways as well. Let's say I'll just delete this one. If you want to delete your geometry which you made, you just right click on the geometry, which is block, and just delete it. So if you there is something known as work plane, where you can sketch your geometry. I mean, just make the 2D of that, and like later you can extrude. So you go to the work plane, then plane geometry will come. So it will look like this. So in plane geometry, if you right click on that, go to the rectangle, put the value there. Let's say 100 by 10. Simply build it. So this one is the 2D version of your geometry. So in order to like give the out of plane thickness, what you have to do is you go to the geometry. Sorry, work plane and extrude. What is that? Extrude. So if you extrude that, let's say, then you can get your geometry. So there are two different ways of making it. Either if you are like working in a simple design, you just click on geometry and make a block or cone or sphere. Otherwise, you can go to the work plane and sketch your design. Right now, I'll delete this one. I'll show you. I hope like everyone is following this. If you have any question, you can ask. So I'll just go to the block and I'll make, let's say, 110 and 5. Yeah. So this is how you make your geometry. So once you like complete your geometry, you have to assign the material, right? uh, okay, I think I missed up. Okay, you can like import, you can also like import the geometry in COMSOL multiphysics. So if you like make your geometry in different CAD software, let's say SolidWorks or Fusion or AutoCAD, you can like import your geometry as well. So you can go to import, right click on the geometry, you just import, and you can import your file, like, so it will be either step file or IGES or other. So yeah, after that you have to assign the material. So if I right click on the material, I'll get add material from library. You just click that. Yeah. So in COMSOL has some already like built-in material properties where you like easily find. You don't need to worry about the material property. COMSOL has that library, and you can just assign the material. Since we are working on MEMS device, I'll go to the MEMS here on the right side. If I click here, if I go to like semiconductor, you'll find many different options like diamond, gallium arsenide, germanium, polycrystalline silicon, single crystalline silicon, and isotropic as well as an isotropic. So I'll be just selecting one type, let's say single crystalline uh, isotropic. So I like all of you to go through like what is like isotropic, or what is an isotropic, or what is like single crystalline or polycrystalline. So this will help you later to understanding the material properties. So I'd like to assign you a homework as a like homework. Please go through go through it. So when you like so before assigning the material, your geometry looks like this. So as soon as you assign your material, it color will change. So it will turn blue. So you will get to know whether material is assigned or not. Otherwise, you can see in the selection box. So one is your geometry. If you click on one, it will turn into green. One is your geometry. So geometry like one, this in this geometry material is already assigned. So if there are like multiple like designs where you want to put different material properties, you just like select the different material. It will come here under materials, and you just click on that, on the particular geometry. So let's say this is my single geometry. If I like click, so I have already, I'll just remove this and remove this. I have like already assigned this geometry as a single crystalline material. But if I like assign another material in the same design, it will get if I go to the first material, which is silicon. So you can see here it will be like over hidden. So you can check from here also, like whether it is like you have assigned the same material, uh, different material to the same geometry or not. So you can check over here as well. So if I just remove INSB, let's say if I just remove it, and if I go to single crystalline again, so there will one will only come, right? That overridden has gone now. So you can check like this. I'll just delete it. Yeah. So here, if you can see the material properties as well. Since I have selected a single, what is overridden? Okay, yeah, thanks. So let's say if I like select gallium arsenide to the same geometry, so this geometry is assigned with like gallium arsenide, right? But I have also assigned silicon. If I click on silicon here, it will show here like one is overridden. So you can like assign two different material in a like single geometry. So from here you can check whether you have assigned the correct right material or not. I mean, like if you have a multiple different parts here, you can assign different material to different parts. So is that okay? You can speak if you have. Oh, okay, thanks. So I'll just delete this one. Yeah. So I have assigned the material properties here. You can also. Oh, okay. Where did I go? Okay. You can also like see the material properties which you have assigned. If you go to the silicon here, under the material, you can just drag down, and you can see the like density of a silicon, Young's modulus, Poisson ratio, everything. And if you want to change, let's say if you want to change the Young's, it is like coming by default. COMSOL has that library. If you just want to change it, you can change as well. So instead of Young's modulus 170, if it is like 160, which which is your material, you can change it to 160, and it will also work. So you can change from here as well if you want to. So let's say if you let's say if you are working in a material where it is not in a material library, what you can do is you just click on materials, right click on material, and you can put blank material. So this one is coming as blank, and you can simply like put, okay, you can like simply put the different values over here. Sorry, that is not coming. Okay. So yeah, you can put the value on that as well, like. So okay, once you like assign the material, so what we have to do is we have to go to now boundary condition, where to apply a force or a load, whatever the like type of load you want to. So just go to the solid mechanics. Since we are working on cantilever beam, I'd be like fixing it one side, this one, which is the orange, and apply load on the other end. So if you right click on solid mechanics, there are many options which will like pop up. So since we are like fixing one face of a cantilever, you just go to fixed constraint. So which is like half blue and half is like white. If you click on that and click on the face, this face, so this one is got like fixed. You can like see the like face number on the selection box as well. So if you fix other side, it will like come how many like faces are selected. So you can also like see which face you have fixed by just like clicking on the numbers. It will turn into green, this. So since I'd be like like fixing this, you can remove other face just by clicking on that side, or by clicking on that number and just subtract. So so this part is fixed now. So there are other kind of fixing as well. Since you are like fixing this face, you can also like fix by to their edge as well. So if you see here, go to edge and fix constraint. You can fix the edge of your design. So since like you want this side not to like move, so you can fix like this also. Also you can like fix the point as well. If you go to the points and fix constraint to that, you can fix the point as well. So the end of the like geometry, you can see the points. Let's say if you want to like fix somewhere over here, let's say at the like middle of this face, so there is no any point, right? So at that time, what you have to do is you have to go to the geometry and go to the like points, more primitive and points, and make the point here, and after that you can like fix to that point as well. So since I have already fixed on one side, what I'll do is I have to apply a load on the other side, right? So in order to do that, you go to the like same like solid mechanics, right click on that and go to boundary load. So let's say if you want to like apply a force on this face, go to the boundary load and select this face like this. You can see. So like if you want to apply a uniformly distributed load, you can just click here and you can like apply the load to any like faces. Since I'll be like applying a total force, so then if you can see here, there's a load type. You there is force per unit area. I want to apply a total force, so I'll be going to total force, or you can like apply pressure on that also. So since this one is like z axis, so I'll give a force or like let's say 10 Newton. So this is like z axis positive. If you want to like want this beam to deform in a like z axis positive, you have to give a load on a like positive 10. If you want to move it downwards, you just have to like give negative. And also it is like you can write your own equation as well in this. As when you like work on MATLAB, you'll write a number of equations, right? So same thing, you can also like write the equation here as well. So according to like, let's say if you want to like give a load after some time or some step, you can do that as well. So once you like assign your boundary load or any like once you like complete the um, assigning boundary condition, so what you have to do is you have to go to mesh. So there are different kind of mesh which is like available by default on COMSOL. So if you click on mesh, so it will like this kind of thing will pop up. So if you go to the element size, there are many options like fine, normal, finer, extra fine, extremely fine. If I just click on normal and builder, so your geometry got discretized. I mean it is like discretized into small elements like size. You can see. So while doing your simulation, you have to like uh, you have to be careful with geometry like mesh as well as your device. mm, Sorry, your geometry will be mesh sensitive. So you can also study different go to like different mesh and run the simulation and see how your result is changing. So if I go to like extreme extra fine, so you'll get more number of elements. So this is called like triangular. You can see the triangular section here. So this is a one kind of mesh, which is triangular mesh. So also you can also like assign your own mesh also. Instead of going to the physics control mesh, you go to user control mesh, and you can play the like size of the element size. If you go to the custom here, you can change the element size as well according to your like desire. So if you like click on right click here, you can like go for like different type of other mesh. Here is like free tetrahedral shape, and also if I go here, sorry, yeah, you can like change the size of that one as well. So please also like study what are the different type of mesh. Let's say this is a triangular mesh. What will happen if I do tetrahedral mesh? And also why the uh, your element size matters. You also like check this thing. So once you like mesh your geometry, so you have what you do what you did so far is you like made your geometry first, then you assign the material on that, then you went to the boundary condition and fix according to like gave the boundary condition according to your desire, and you completed the mesh also. So what you have to do is just study, run the simulation. When you go to the study, since you have selected the stationary study before, so this thing will come and just compute that. Either you can compute from here or just go to study one and compute. It will run and you will see your deformation on here, right? So since we have like given a like load in a positive direction, so I mean in the z axis, so it is like deforming in this fashion. So if you want this one to move down, what you have to do is you go to the boundary load and give the force -10. So it's just like in a negative axis, and run it, and now it will come down. So this is a like contour plot, and you can see the stress stress. Since we have like fixed here on this end, you'll there will be a maximum strain here, and the other end, this is a free end, and there is like almost zero bond masses stress here. So let's say so this is the like bond masses stress plot, right? If you want to see the see the deformation, what you have to do is you have to go to the stress, solid and volume, right? So if you see here, you see the one masses stress. Solid does it's the expression for that. If you go to the expression here and see this one, two triangles like facing opposite to each other. One is in red and another is in green. You click here and you go to there are like different things, like different results which can plot. You go to solid mechanics here, and you go to the displacement and solid dot dips. If you go here and plot, you can see the maximum like displacement here. So this is like how you plot your results. Let's say since you have applied only one load, right, which is F, so you can like yeah, hello, any questions? Yeah, sorry. So you can as I told all the earlier, you can put your expression here as well, right? So let's say since you are applying a force here, what will happen if I just write F instead of 10? I'll just write F. If I just write F, it turns into LO. See, you can see if I just put my cursor there, it will show unknown variable. So that means you have not defined F. So if you want to define F, you can go to the at the top, it is like parameter. Click on that and give a name F, and how much you want to give, let's say 10. And if you write something inside square, you can write something inside square box, so you'll be writing your units there. Force is in Newton, so if you write N, it is assigned now. See, your F is like defined, which is like 10 Newton. So if I come to the boundary load again, and you can see now it changed into black in color. So it is like defined. But if I write something else which I haven't defined, so it will say unknown variable. But what I already defined is F, capital F, so it will take that value. So I have defined the force in Newton. So here the total force will be in Newton. You can see the unit here. What will happen if I put something else instead of Newton? I'll put Newton per meter. So F is defined in Newton per meter. If I again come to boundary load, see, you can see it turned into LO. If you just put your cursor there, it will say deduced unit is Newton per meter and expected is in Newton. Since it's a force, its unit is Newton. So you just go here and change again to Newton. So this is how you can define your load. Also, if you see here in study, if you right click on the study, you'll be like finding many different options. You can see parametric sweep, function sweep, material sweep. So now what I want is, instead of giving only one load, I want to like check different load. I mean, I have like given 10 Newton. I want to see the deformation from 1 Newton to 10 Newton, or 10 Newton to, let's say, 1000 Newton. So what for that, if I want to perform that simulation, what we have to do is, you go to the study and right click on that and go to parametric sweep. If you if you click on that, this thing will pop up. And now I want to like sweep my force from 1 Newton to 10 Newton in the interval of, let's say, 1 Newton. So if I go to plus here, I go to plus, so I can directly put my value in a parameter value list, or I can just go this one, range, and I will start from, let's say, 1. I'll at the step of, let's say, 1, and stop at, let's say, 10. So it will, what I did is, now it will like so now my boundary load start from 1 Newton at an interval of 1, and it will stop at 10. So I'll just add it. So range 1 1 10. So this one is starting, this is like at the interval of that, and 10 is my final. So if I just compute it, so you can see that deformation here. This is for 10 Newton. If I go to 1, okay, deformation, you can see. Okay. Yeah, sorry. Yeah, so if I like go to 1 Newton, so this is the maximum displacement here, 1.8 into 10 power 4. For 2, 3.5 into 10 power 4. It's changing, right? So as your force increases, your displacement will also increase. If you see this plot, so if you want to, okay, this the deformation plot is not noticeable. So if you just go to volume and on the deformation, so this is a scale. If you see the scale factor, so this is my scale factor, and if I change it into like make it like larger, so you'll see your displacement like this. So this is just the exaggerated image. What I did is I just changed the scale in order to see the displacement, which is like notable. So let's say this is the displacement for one Newton. So this is for 2 Newton. This is for three Newton. So for 10 Newton, let's say it will be like this. So this is just for visualization. Okay, if you want to look like, okay, this one doesn't look uh, like good, I'll just type 1 slot. Okay, right. Yeah. So this is my displacement at 1, and if I just keep on moving, so this is the maximum load, which is 10 Newton, and this is your maximum displacement. You can also like make a beautiful animation in COMSOL as well. So this is the result. So what I'll do is I'll like make a animation of this. So what I'll do is I'll go to the any animation which is on like on your right corner. Simply click on that and go to player, and you come to the left hand. You can see export animation is here, and it was played once, and yeah, you can play from here. If you want to like play continuously, what you will do is you just repeat, go to forever, and just play. You can like see the change in like deformation according to the force. You can see the force over here: 1 Newton, 2 Newton to 10 Newton. So once you like see this thing, you can also like export this one. So in order to export, if you want to export the video of this, so what you have to do is you go to the target over here and play in place of player, you click file, and if you want it in GIF file or flash or something, AVI, it's up your choice. And let's say if I want in GIF file, I go to browse, so it's here. I go to browse, and I'll just save wherever I want. This I'll save it the GIF file. So save it and export. So it will get exported. So you can like extract the video file or the animation file like this. So this is how you do a simulation in COMSOL. So if you have any questions before I move to another example, please let me know. No questions? Okay. So now I'll do another example, which is eigenfrequency analysis. So I like you to go like to the theory, like what really is eigenfrequency analysis and why it is important. If you are working on, let's say, accelerometer, it will be very helpful. You should know everything on that. You have to know what is like resonance, what is resonance frequency, all of those things like come into play on that. So I'll again like take one simple example and see like show you very quickly how to perform eigen frequency analysis. So after you like complete this simulation, you can just save your file. Just save it. Okay, you can just save. And now I'll like perform one eigen frequency analysis, and I'll tell you why it is necessary. So now I have already saved it. Now I'll go to new file, new, and model wizard, 3D. Okay, this one I'll do 2D. I have already given a 3D example. Okay, let's go to 2D. And again, since you can search here, again, if you just okay, you have to like, sorry, first select the physics. You can say model wizard, 2D. Since it comes under solid mechanics, you click solid mechanics and study done. Oh, okay, it has already done. I'll again go there. It will be easier for you. So if you just add add here and study, it will go to the another like physics. But if you click on done, you have to like uh, again like choose the study from there. So it will be easier if I just go to study. And now I'm performing eigenfrequency analysis. So it will show you like what is like exactly eigenfrequency. Like it will give a brief introduction here. The eigenfrequency study is to complete eigenmodes and eigenfrequency of a linear or linearized model. So just click on that. I have already saved that, and I'll say no. So again, like this is how your window looks like once you open like set up COMSOL. Now Now the first thing is you have to make your geometry. So you have to choose your scale again. Let's say I'll work in micro scale only, or millimeter, okay. And I'll just go to the geometry. What I'll do this time is I'll just uh, make one beam, and fix to both side both side and see how this beam will like vibrates. Okay, so this is the example which I'm like showing right now. So you go to the geometry again, and you go to the, like, since it is a 2D geometry, so you go to rectangle or square. It is of your interest, what type of like model you are working on. So you go to the rectangle and just give the input 100 or 10. So my like geometry is ready. I had made a uh, this thing rectangle with 110, or I'll make it little bit thinner. After once you like complete your geometry, you have to assign the material again. I'll just quickly do it. Add material and recent. If you go to the recent material, it will show whatever material you have worked on recently. I'll be choosing silicon. Once you like select the material, it will convert it into blue. If you do not select the material, then it will be like your geometry in a gray. So once you like select your material, after that what you have to do is, since I'll be like fixing at the both ends, I'll just go to solid mechanics and fix constraint. Since it's a like 2D, you won't see a face on the other side, so you have to fix on the edges. So fix on this side and this side. So I'm like I have fixed here and here, and this will be like free to move. So if you like click here, you can like fix any side of your interest, and it will like pop up here. So since it's a eigenfrequency analysis, we will be seeing its different eigenfrequency and its mode shape, at what frequency, what type of mode shape it is like it will have. So I'll just go to the mesh now and give a like type of mesh. Okay, right now I'll choose finer mesh and builder. If you like, you should like always careful of your mesh element size, because it is totally dependent on your result. So it's always like better if you do a mesh convergence study as well. See, choose the different mesh and see how your results is varying. Okay, once you like select, choose your mesh, you go to the study, and if you select here step 1 eigen frequency, this thing will come. So since we don't know at what frequency it will have a corresponding mode shape, so I'll just turn off this. And how many different mode shape I want, let's say it is like desired number of eigen frequencies. I'll just click here and take it as like 20 different mode shape. So there are many different solvers here. So we'll check this one later. You can explore what this solver exactly means. You can always like check those things. So once you set up the desired number of eigen frequency, and then you just have to like click compute. So our like results came now. So this is the first mode of your geometry. So it looks like this, and you can see the eigen frequency here as well. So eigen frequency of this first eigen frequency is 4505.1 hertz. So if you click on the plot and on the like plot next, you can see different mode shapes. So this is my another mode shape, and your frequency is like changing according to your mode shape, right? So this is like eigen frequency analysis. So I want you everyone to learn about what is like eigen frequency, or what is like more safe, since all of you are from different background. First, like this thing are like totally mechanical, I'll say. So please go through the like basic of that that one, and it will like help you. You won't be like totally blank. And I think what so after that, let's say I want to like see this one vibrating. So what I'll do is I'll go to the any animation here and player. I can see how like if I click it forever and play. So this is my first mode. So if you like actuate this beam at this particular frequency, eigen frequency of 4505, this is how it will vibrate. So this is called mode shape, and this is and the eigen frequency. So at this particular frequency, your beam will vibrate like this. And once you can, as I told earlier, you can also extract this file, which I already showed you to. Okay, what decide the magnitude of vibration? So yes, your amplitude will decide the magnitude of vibration. I mean, how you are like vibrating. Let's say you have like, this is your frequency, right? So when when your beam, this beam will vibrate at this mode shape. It will vibrate in this shape when your input like frequency is like 45,005 hertz. There is something called resonance. I think you most of you already know. And you like it, if your beam resonant frequency matches external frequency, then resonance happen. At that point, you'll get the mode shape. So you can like let's say in accelerometer or gyroscope, since it is like vibrating device. So let's say gyro, it's a active sensor. It will be like vibrating throughout its life, right? So it depend upon the mode shape, like mode shape which you are vibrating. So I mean, magnetic amplifier. Yes. So at like resonance, your your device will like fail. You can like see the many like building, tall building, or the like bridge. So they fails like sometimes because of the resonance. So they always like try to make those kind of like big bridges, houses, far from their resonance frequency, because at resonance frequency your amplitude will be maximum, right? But it is like helpful in MEMS device. Let's say gyro. In gyroscope will be like vibrating at its resonance frequency. So we'll like extract the change in capacitance value when the angular rotation is given. Yeah. Anything else? Uh, any questions? Just check the chat. Okay. So this is the example of eigen frequency analysis, and this kind of analysis is helpful when you are designing accelerometer or gyroscope, which we will be like talking later on detail. So right now I'm just giving a brief idea how to like perform various simulation in COMSOL. So now what I'll do is I'll give one example on electrostatics. What I'll do is I'll take as Venkatesh already like talked about electrostatics, electrodynamics, and all the like circuit thing. I'll just give an example of parallel plate um, actuation, how it happens, or how you measure the capacitance between two parallel plates. So I'll just show you in COMSOL how to do it. If you have any question till now, please let me know. So I hope you all like understood this one. If you have any question, you can always write a mail to me. So I just save this one as well. Uh, the- okay, now what I'll do is I'll do one do do like parallel plate example. So I'll just go to new model wizard. I'll just do 2D example and go to like, see here, now you have to go to, if you go to ACDT, sorry, ACDC and electric field and current, you can see electrostatics here. Since I'm just measuring the, trying to find the capacitance between uh, parallel plates, I'll go to electrostatics here and study, and it's a like stationary simulation. Just go there, right? So this is how it looks like. So I'll again like change into micrometer. I'll be like working on this scale, and I'll quickly make the geometry. So what I'm doing here is I'll just delete this thing. Delete. So as you all I hope all you have studied in high school about capacitance or the capacitance of a parallel plate. So what I'll do is I'll just take two plates and try to find the capacitance between them, right? Okay, so you can so this is how it looks like. So here it's like it's a electrostatics, right? So please uh, please like find why it is called electrostatics. So I like assign this one as an homework. Why electrostatics? There is something known as electrodynamics as well. I think you have already studied in earlier lecture. So I like everyone to work like study what is electrostatics and why it is inferred as like electrostatics. So I'll just quickly make a geometry. I'll just go to rectangle. Let's say one. I'll just take, okay, 480 and 5. Let's say height is 5. So this is, I made this geometry. I'll just make it in center. And now another plate, and the gap I'll take it 10 micrometer. So I want the another geometry here, right? I have already made one. So what I'll do is I'll go to the rectangle again. Since it is a rectangle only, I'll just duplicate it. Right click there and duplicate. Otherwise, you should go to the geometry and again make a rectangle. So if I just duplicate it, same thing will come. Now I want to change the like location. I want this plate moving uh, upwards, and the gap is 10. So I'll be like moving this one upwards. So I'll just go type -10, let's say. Sorry, plus 10. If I try plus 10, it moved up, right? But I'm taking the position as center. I don't think it the gap is like 10. It is just 7.5 something. Yeah, it started from 2.5 till 7.5. So the gap is only like 5. If I go right here 15, it will move. Now it became like 13 or 12.5. Okay, anyway, like let it be this way only. So this is the gap between the plate. So what I want to do is I want to find a capacitance between two plates. So since here at the middle there is nothing, so I want to so okay, I'll do that one later. So I'll go to the material and I'll assign the material as well. Don't we need a Z time? No, this is a like 2D simulation, right? You can see the out of plane thickness here in 2D as well. So since I'm working in 2D, so you can just remove that one. Is that fine? Yeah, if you have any question, please let me know. This is a 2D simulation. Yes, okay. So in 2D simulation, you don't, so COMSOL won't take out of plane thickness, but that will be assigned. If you see here at electrostatic and go to out of plane, you can see the dimension here, and you can change it from here itself. Okay, yeah. So I already made a uh, two parallel plates and I'll just assign a material, add material from library, and just go to the, I'll just put, okay, silicon again, let's say this one, and in both like plates, it got assigned. So if I want different material, let's say if this geometry is something else, if I want to put assign material different material, you can just click, like go to another material and click it again here, and you have to like assign in that manner. So here I have already assigned uh, silicon, and this is a stationary analysis, and we are just measuring the capacitance between two plates. Here nothing is moving, I mean your geometry is not deforming, right? So you don't worry about fixing the things. But if you have selected structural mechanics, you at the time your voltage will pull your beam, so at the time you have to like fix that thing, so be careful on that. So in parallel plate, what will happen is there should be one dielectric medium as well, right? So here I want to like select this one as an air, but if you see here outside the like space, in the space that like you have to like constrain your design, right? So if I want that my medium as an air, how will you do? You can't simply just select air and air. Let's say if I go to the material library, if I air, so build in air will come, but where we like assign, you can assign in the space, right? So what you have to do is you have to make a bounding box. So I'll just go to the geometry, and again rectangle, and I'll make a bigger box, let's say 800 by, I'll just see whether it will fit in or not. I'll center. So this is my box. If you want it bigger in size, it's your wish. But there is a like there you might have a question, how much big it should be. What if I just make, let's say 50? What will happen if I make it this much smaller? So it should be symmetry, okay, like both sides you try to make it equal. What will happen if I make this one small or large? Let's, and how you will know like what might be the actual size of that. So you have to make a bounding box so that such that your electric field on the edges, I mean the bound at the bottom of the, at the like boundary of your bounding box should be like 0, so there won't be any effect of it. So I have or like in some like book, what I found was if you just make your bounding box like 2 times of your dimension, it will be fine. So you can check that one as well. What will happen if I make a smaller boundary box and I keep on increasing the size and see try to match with your analytical results, and see at what point it matches. So I have like made this bounding box, so I have to define this one as an air. So I have already like selected air here, so I have to click this box. If I click this box, one has come, right? So I haven't like selected my silicon material. You can see here they are in green, which are selected. So this is one. But if I like select this one as an air also, like it will come in blue. So if you go to the silicon, it will show overridden. So you just remove two, and this one, your bigger box is your uh, you define as an air, and if you go to silicon and the blue things, so these two plates are defined as silicon. All right. Okay. Now what I'll do is I'll go to electrostatics. If you see here, there are charge conservation, zero charge, and initial value. So in parallel plate acquisition, what will happen is you have to like give assign or like voltage as one plate and ground it another, right? So if you just right click on electrostatics, so you can see terminal, electric potential, initial value, everything, right? So you just go to the terminal. So if you see the box here, it's like full blue. If you see here, they are like it is not filled with blue, right? So what will happen is if you click this blue one, you can see this terminal and this one as well. So if you click this blue complete like full blue one and select here, your entire geometry will be selected. But similarly, if you click on the terminal here, which is like partially blue only at the edge, you can select the edge. So that is like between like whole your geometry or like your this thing or the edge. So right now you can do it either way. You can your results won't like vary. Okay. So I have like, so this is my terminal one. So what I'll do, so if you click on the terminal, you can see terminal name and terminal charge. Since I'm assigning voltage in this, I'll just go to voltage, and I have assigned my voltage, right? Since uh, capacitance is epsilon A by D, your input voltage won't matter to your capacitance value. So I have just assigned one volt, and I have to like ground this one, right? The another one. So what I'll do is I'll again go to electrostatics, and there is something called ground option is there. Either you can like just ground your another terminal. Okay, another one. Oh, sorry. Like this is grounded now. Otherwise, what you can also do is I'll just delete this. Since so ground means like your voltage is 0, right? So you just like go to the terminal and select the another one and assign yeah. Oh, sorry. I mean, don't you need the diameter? Okay. So I'll show that one as well about the z dimensions. So you can like just put your voltage 0, right? So yes, you can put your z dimension here out of plane thickness. So in 2D simulation, what exactly happens is it won't consider out of plane thickness, so that you'll get your result very fast. But if you are doing 3D, it will take everything, so it takes time. So in 2D, your computational time will be like very less. So you can just put, okay, if you want out of plane thickness as well. So let's say I'll put out of plane thickness 10 micrometer, 10, and you can also, so since if you see here out of plane thickness, it's in meter, right? Let's say what if I want in scale or micrometer scale. You can just like type your this thing square box, this one and this one. Oh, sorry. So inside that box, you can just write your scale, like what we exactly want. Let's say Sorry, yeah, So it will work, right? But if I write something else, let's say t, it will appear in yellow in color. So your dimension, your deduce unit doesn't match. So since the like your dimension will be in meter, or micro, right? So t has no unit. So either you have to write, if you want it in you write Let's say if you want it this one in micrometer, so you just write it will take u as a micron, like in that, and you can just write it will take. So here, see, you can see there is no error. But if I write something else, let's say, it will come yellow in color. So when you put the input, and you should be like careful here. If something comes in yellow, you should be like careful about it. So let's say I'll keep it in micrometer. So so what I did is I have first made a like geometry and assign a material. I've also like assigned my dielectric medium, which is air, and material silicon. And in electrostatics, I have defined terminal one, like voltage, and also like ground it, right? So what next step is like meshing. You go to the mesh and you just go to element size. It's a like physics control mesh. So COMSOL will do everything. So if you want your own mesh element or mesh size, you can play with that also. So after that, you go to the normal. So if I just mesh it in normal, what will happen? You can you can you can see the element size, different element size here. So if I just go to extra fine, let's say, and build all, so it will reduce. So it will be your geometry is like discretized into smaller element. So like it is, so that it is always like better to like do the mesh convergence study also, because most of the time you might get a false result uh, because of like mesh element or the mesh type also. So so you should be like careful. So I can go to extremely finer mesh if I want my result very good. I mean close to your analytical like formula, or let's say close to your expected results. But what will happen if I make it like go make the mesh finer and finer? One thing is like one important thing is like computational time. It takes a lot of time to compute if you make element size like finer and finer. So you also need a very good like CPU or like very good computer in order to like do such simulations. So for a time being, I'll just put extra fine. Okay, for now it will be fine. So after I mesh it, I'll just go to the study. Here you don't need to do anything, study and just compute. So you can see this is the electrical potential plot. So we gave a like potential at the top plate. So here it is maximum, and you can also see the electric norm, like how the field diameter generated and everything. So here I want to see the capacitance between two plates. So what I'll do is I'll just click on derive values, global evaluation, and you can since you know that uh, your formula of like capacitance, it is like either epsilon A by D or Q by V. So if you see the expression here, you can, if you go here on blue and green and red uh, color shape, you can go to electrostatics and see different like what you want, right? If you go to the terminal, you can see the uh, terminal charge and terminal voltage. So terminal es dot q01 1 is like terminal charge at your uh, this one, at your first this thing rectangle, first plate, I mean. So terminal 2 is like this one, second one. So go to like global evaluation. So either you can find the capacitance like this. There is something known as Maxwell capacitance. If you evaluate this one, I think in table it has come. So this is your capacitance, 4.4396 E minus 15, right? So I want everyone to like study what is like, I think if I'm not wrong, you might heard first time this one, what is like Maxwell capacitance. So it's a like big topic. So I want everyone to go through it and learn how like COMSOL COMSOL like do Maxwell capacitance like example. So please check like what is like Maxwell capacitance. Okay, so this is the one way. So another way is like, as you know that capacitance is also like Q by V. So you, if you like go to like terminal one, so which is like charge, terminal charge Q, if you select this one, so this is your terminal charge. So if you click on the expression and divide it by voltage, which is your terminal voltage of charge one, so I just copy this one. So you have to write in this manner only. So let's say if I copy this one, and instead of Q, if I write P, because I know this expression already, because I just like did it from here for voltage one. So terminal voltage one is this one. So if I just write this expression here, so COMSOL will by default show you the unit, that is farad. But let's say if you do some mistake here, let's say if you write different expression, let's say L, so there is no unit. It means COMSOL didn't recognize your expression. So you should be like careful. If I write something else or A, there is no unit here, right? So you can check whether the expression is correct or not. If it's, I have to write V, capital V. Now charge by voltage is capacitance. It came in farad. Okay. And if you simply evaluate it, you can see here 4 point is this one in the table 4.3996 E minus 5. So you can either find the capacitance value by this, by writing the expression. You can write your own expression. Also, if you want other thing, or you just measure the Maxwell capacitance. So this you can also okay, one important thing which I missed is you should always be careful about your result, because COMSOL is I'll say it is like a black box. Whatever input you give, it will, if you do put the right boundary condition, it will give the results. But that doesn't mean your results or the way you are doing is correct. So it is always better to calculate it analytically and try to like see where like your FEA, any FEA tool results is matching with your analytical results or not. So if you just, you can also like, for this example only, you can just find the value using capacitance equals to epsilon A by D. I think yeah, you will like get your results near to that. So your result might be off by some 3 or 4%, but it's like still like 5 or 6%. I'll say it will be fine. So you should be always like careful on that. Always like try to, don't just run the COMSOL simulation. It might be like wrong in the process also. So you should be like careful, and also like try to match your results with your analytical results and all. Okay, so this is the COMSOL, few COMSOL example which I wanted to show you. If you have any questions so far, please let me know. Any questions? Okay, so now what I'll do is, so what I planned was to, I did structural analysis, eigen frequency, and electrostatics. We can also do one. Okay, I think we are running out of time. I have some other things to show to you as well. So maybe I'll like try to organize another class. I'll request Carlos to like conduct another class, and there I'll show you how electromechanical coupling happens. I mean, let's say this COMSOL. So this is only electrostatic, right? So you are like giving a voltage, and this this is your ground. You're applying a voltage here. This will, your geometry where you have given the voltage will deform like this, right? Something, okay, like this. Because your another thing will, okay, if you can show us one example lateral. Okay, yeah, sure, Sumit. I'll try to do that one as well. So you can, okay, yeah. So this one will like deform like this, right? Like this, it will be deforming because your it will like try to this plate will try to pull this one. So it's like when I like give a voltage in this electrode and or the your geometry and give a like make it ground to this one, so your this plate will try to come down. So it's a like coupling between it's like coupling is happening. What I mean to say is you are applying a voltage and try to see the deformation of this plate. So it's like electromechanical coupling, right? So that is another type of simulation. So we'll do that one in another class maybe. So now I want to like talk a little bit about electrothermal actuators, since I think many of you might be like interested on working on that. And in next class, I'll also like try to explain about accelerometer. And I have a like MATLAB code, which is like the Beam code written by Professor G.K. Suresh. So you can also try to match your result, like MATLAB result with your COMSOL result. So it will be like, I hope it will be more interesting in that manner. So so as I like discussed earlier back then like 2019, many different students work on different devices. At the time I also worked on this design, which is like thermal actuator. I'll be like discussing on that only now. So I just, yeah, okay, where is my, so let's go to electrothermal actuators now. So COMSOL example I'll be like showing you more on next class. And now, so I think you all of you heard about like MEMS sensors, right? Micro electromechanical systems, but only you have heard less about electrothermal actuators. If you see today market, there are very less group who works on thermal actuators, but in sensors group there are a lot of people, a lot of like sensors group like who work in many different kind of sensors. But in actuator side, electromechanical actuator side, only like few groups works. So mainly there are like many different kind of actuator. Out of them, electrostatic actuator and electrothermal actuator are the famous, like they are very popular. So today we'll be discussing about electrothermal actuators. So what is electro, like as the name already suggests, electro and thermal and also actuators. So something is happening there, right? So we'll be discussing about that. Let's say if I take a beam or a like bar or a rod, this one, what will happen when you hit it? It expands, right? So it will expand this way. If you do not fix anywhere, it will expand this way, this way, this way, everywhere. But what will happen if I just fix at one end, this end, and give apply a heat? It will expand in this way, right? So my original length is L, and you will have a you will have an extension on like which is like delta L. So what will so this is what exactly happens when you heat it. But how much it will expand? Let's say I'm like giving some amount of heat, and it I told like it will expand, but by how much? So it is so expansion of a bar of length with delta L, it's alpha delta TL. Alpha is the thermal expansion coefficient and T is the temperature change. So since in like MEMS devices, silicon is one of the famous material, and like most of the like people works on silicon only. Also, I want everyone to look on into like silicon and why silicon. If you see the history, the first MEMS device was made in some other material. Please check what is that material. Okay, so it is interesting. And after that, like silicon came into the picture, and till now we are in silicon only. So please check why we move to silicon. So if you take an example for like silicon, also it has a very less thermal expansion coefficient. So I think so it is in the range of 10 power minus 6, 2.2, 2.5 into 10 power minus 6 range. So it will like it will just move, it will just expand little bit. So what if you keep on increasing our temperature, it will expand more. If you keep on increasing delta T, it will expand more. But this is a like actuator, right? We'll be like using it for something, and if you just hit it, uh, uh, we and also it is a very uh, small like device. We can just hit it because it will be like melted and it will be like gone. As I saw the example earlier, that an animation of thermal actuator which we had designed, we actually like keep on giving the voltage, and it like it fails at some point. So what I want is I want a maximum displacement, but I want to take like I want to have delta T as small as possible. So what we can do exactly? We can like play with the length. So in our context, like design is something we have to do with the geometry. So and also it is not just changing your dimension. So if I make this long beam, so that, or like if I just change like increase the temperature of like working temperature, it might not work. So we have to like work on the like design as well. So what will so this is how it looks like. Let's say this is my, so blue part is my geometry, and these are two pads. So it is also known as like bond pads, as we are like as we fix wires bonding to apply a voltage. So this is how your design looks like. So what will happen if I just apply a voltage in this? So current will flow, and because of some what will happen is like current will flow, and joule because of joule heating, it will like it will heat it, right? So please check like what is joule heating, because it is like it is important for us, because of the, as I told, because of the joule heating, it will heat up, your material will heat up, and there will be some deformation, like change in like your length. So in this design, if you check this design, if I like fix at 2 points and give a voltage, definitely it will like deform. But which side, can you please, can anyone please tell which side it will like deform? Anyone please? It will like when you supply a voltage, current will flow, right? And joule heating happens, but and it will expand. But uh, in which side it will like, how the deformation will look like? It will be either, I'll just make it okay, highlighter. So it will be like this, either like this or like this, right? So it will deform in this manner, either deformation will be in this manner or this manner, but it is like very difficult to predict. It's something like buckling, so which is like very difficult to predict. So this one we act as a actuator, but this simple design can act as an actuator, but we don't know which side it will like deform. So I'll say this is a very bad design. We don't want it. So we have to like play with geometry and the boundary condition where you are like applying a voltage, and like where you are going to fix, and also the material choice. Uh, so and I, as I already mentioned, place of applying voltage. So let's say this design we are not sure in which in at what manner it will define or deform. So what if I make this geometry non-uniform? I mean non and non-uniform in the sense, instead of taking a single uniform beam, if I take it like this, what will happen? I can as I what we can do in this is, so since the geometry is not uniform, heat is like going to be non uniform, right? Here there will be some heat here and some different like heating here, right? Yeah, any questions? Hello. Okay, I'll just check. Oh, okay. Yeah. Oh, sorry. Oh, is my so so geometry will play a important what I am trying to infer is geometry will play a important role here, how it will deform. So after that, so you have like realized that this kind of geometry won't be working, won't be suitable for this. So there is something known as uh, bend wing actuator. This is I'll say this is one of the very oh, what is this is one of the very clever design. Instead of making a single beam like this straight one, the researchers what they did is they make a like bend size, bend wing electrothermal actuators. So if I make my beam in this manner, so what will happen now, in which side it will it will like deform? Can anyone please please I will just see the chat. Deform upwards. Yes, exactly. It will deform upwards because see here. So everywhere it will get like distributed, right? So how it will deform is, I'll just, where is the highlighter? Okay, it will be deforming like this. Oh, sorry. Eraser. It will deform like this upwards, like this. It will sorry for my drawing. So it will be like moving up. So this will the deformation will be also dependent to your angle made by two beams, this theta value. And for a, so if you just play a simple geometry, you will get to know which side it will deform. I mean, you can predict a deformation which will be like suitable for a design. But instead of taking this shape, if you just take a straight beam, you you don't know like which is in which way will it will going to deform. So so we already know it will be like deforming in this way, up which is upwards. So what if instead of making a single one, what if I put a array of a beam and like joins everyone. So if I make an array of a beam and join it, so I'll be like getting a maximum, since the deformation displacement will be same. What I'll increase is what will increase is the force like generated by this beam. So from this design, like we move to here, because here we'll be like getting a more displacement. We can also check this one by analyzing it. What I all want from this slide, what I'm trying to tell is design plays an important role here, and also it can like also you can like think about for different applications. So instead of like, let's say this is one of my design and uniform. Similarly, if I make a same like actuator, but if I just change the cross section, you can see here, if I just uh, change my dimensions of the beam, now what will happen? So what do you think, whether this the first beam like smaller width, which has a very smaller length, will it react first, or the bigger one will react first? I mean, which one will go, since it will be going upward, but which one try to go up at first? Uh, yeah, okay. So smaller, sorry, I just, okay, bigger one. Okay. No, here in this case, the smaller one will try to like respond sooner. Why this one? I got another one. Yeah, okay. Why smaller one? Because heat will be higher for a shorter beam than the longer beam. Why? If you see the formula, resistance resistance formula, which is rho L by A. So here the length is small, right? Length is also small, and your area is also small. So your R will be less. Similarly, P equals to B square by R. So if your R is less, your P or the heat will be more, right? So a smaller beam, heat will be more, so it will try to respond first. So after some time, it will be like longer beam also will get heated, and uh, it both will like contribute equally. Okay, below goes upward. Sorry, I cannot see. Okay, so this is just the design. What I'm like trying to explain what will happen if you just change the designs, play with the dimensions. So similarly, if you put it in this fashion, what will happen now? As you know that this one, the shorter beam will try to move, uh, like try to like respond first. So what will happen? What will be the overall displacement here? So okay, let's say if I take this point, what will happen here? So at first, what will happen is this beam, shorter beam, will move down, and after that, after some time, your longer beam will try to push up, right? So you can, so I took this example from one of the paper by Suresh, GK and Suresh. You can check that one, or otherwise I'll also like share that one. So this is the like simple various designs which I'm like talking right now on electrothermal actuators. Similarly, this is one of the simple example of a electrothermal actuators, which you can try it in COMSOL also. Like if you're looking for simulations, you can try this one as well. Okay, is that what are the applications? Yes, so there are like many application on this. So people use in a micro robots, or as a like most of the like application are switch. They can like we can make it work as like as a switch. So in a like micro robots or something like that, they will use the thing. Yeah, so if you can also like see this example in COMSOL as well. Otherwise I like I'll be like teaching you in a next class. So here I'm like giving a voltage here, and this is another one is ground. So in which manner it will bend? Okay, highlighter. It will be bending like this, right? So similarly, what will happen if you make two ground? You ground it here, you ground it here, and you ground it here. What will happen? Now the current will split in two and goes to the ground. So it will bend like this. Oh my, sorry. So it will be like it will bend like this downwards. It will bend downwards. You can also like check this one in like console as well. So what I'm like trying to explain in this is, you can first thing is like you can play with your dimensions, with your geometry, and like make it like deform or displace according to your uh, application. And also you can play with the boundary, different boundary condition. So this is one of the another example. So this was done by I think Howell in US. So this is one this paper like shows a very interesting results. So they had like considered convection and radiation as well. What I mean here is, when something get heated, it will try to like go release, right, transfer from this way, or anyway it will like con convected or radiated, right, some of the heat. So but if there is no convection or radiation, how it will deform? It will be like deforming in this manner. Okay, in this way, sorry. Yeah, it will like deform like this. But if you like consider, so without convection or radiation means there won't be any heat transfer from this body to outside surrounding. But similarly, if you consider convection or radiation, where the heat will be like passing from each boundary, how it will deform is, it will deform like this. So this is one of the interesting example, and what they were like trying to show is, you have to put the right boundary conditions, because in a like real device, there will be a effect of convection of convection and radiation as well. But many people won't like consider it. So this example like basically highlights the modeling, not only like conduction, I mean the heat transfer in the to the in body only, inside in the geometry only, but also convection and radiation. So these are the like, so I'm right now I'm talking with the design point of view. So this is how we design different let's say thermal actuators devices, and like predict the displacement or the deformation of our interest, just playing with the geometry or boundary and or boundary condition and all. So what I'll do now is, okay, I have a I'll just I have a like as I showed earlier. We did a different kind of simulation in COMSOL. So what I'll do now is I'll just try to like take an example of bend beam thermal actuator and try to do it in MATLAB. So this code is like generated by Professor GK Ananda Suresh, and I'll be like sharing this code to you as well. First, I'll just close COMSOL and open MATLAB. Yeah. So if you have any questions, let me know. Yeah, yeah. Okay. Oh, okay. I'll just show it quickly. So I'll also like share the I have a MATLAB this code MATLAB manual with me. I'll just so like run this one very quickly, and like in a next time we can do that one as well. So I'll just go to quickly. So this this is a bend being electrothermal actuators. So if I just take it, so if I just discretize it, like in a code, we have to like put different values. So if I just put it in this fashion, so this is my element one. I can take this one as element one, and this is the another element. Okay, so this is my node one. This one is node one. The joints, all the joints I'm taking as a node. So this is a node one, node 2, and node 3, which I have shown here. So this is my node 1, node 2, and node 3, and these are my element 1 and element 2. So I have a different inputs where I have to like put an input. Let's say, for example, source. If I go to the source, I have put 1, 3, and 10. So one is basically the serial number. 3 is the node, which I just explain you. Three is the node, and 10 is the voltage which I am like giving. So I am like giving a voltage on in 10 on like 10 volt, and ground is 1. Okay, so this is source. So after that, if you go to the temperature BC. So one is the again serial. So this is the like element serial number, and these are the this one node 1 and node 3, and I'm defining temperature at 20 degree in node 1 and node 3. So similarly, if we open element is here. So if you open this one is the serial number. Yeah, 1 is the serial number, and 1 and 2, these two are nodes, and I need a like various value, right? I'm like defining my geometry here. Length, this one is width, this one is Young's modulus, and resistivity, and other value. Okay, we'll do this in next. I'll explain more about this in next class. What I'll do is I'll run this one and show how the code look like. So I'll just go to the MATLAB. I'll also be sharing the manual, so I'll share the manual as well as the code, so it will be helpful for you. So this code is like automated. You just need to run, and this is as I mentioned, this is like, okay, what is the question? Can we? Yes, I'll be like teaching on accelerometer design as well. So I'll do I'll also like run I have the accelerometer files. I'll will be working on that as well. So this is my main file, which is like master control. If I just click run, yeah, okay, sorry. If I just click run, you will be like getting okay, this is the electrical analysis value. So I'll just show it just now here, and later we'll discuss more about it. And if I just click enter, it will automatically like give me the like thermal analysis value. As we have like, as I mentioned, we gave at one temperature 20 degree at node 1 and node 3. You can see the 20 degree here, and here it's like maximum 75.4. Similarly, this is the thermal elastic analysis value, how it is deforming. Similarly, this is the deformation value, like as I mentioned, because of the joule heating, it will deform, right? So this is this dotted line is my original one, and it is like deforming. Red one is the like deform one. I'll just zoom in. Yeah, you can see this one. So this is my master control value, and we have other like script as well. So let's say you have to like work on thermal, like we have a code for thermal. So everything related to thermal, it has that value. And if you see the current, you okay, not this one. I think I have to open. I didn't open that another one. Okay, I'll just quickly open that. Electric. Yeah, so electric one is here. So all like the formula, like resistance equals to rho L by A, all this thing are there. So what I want you is just play with this code first. And if you want to work on thermal actuator, we can work like we can talk in detail as well. So this is just an example I'm giving. And in a next time, what we'll do is like, as I showed you this MATLAB file, we will try to do the same simulation in COMSOL, and try to, let's see like whether this simulation result will match in our COMSOL value or not. Also, I have a like code for accelerometer. You can also work on that. I'll teach you in next class, if you are like interested working on that. And also like I'll teach you more in details about thermal actuators. So if you have any questions, please let me know. Yeah, any questions so far? Okay. Yes. We can design full uh, this thing accelerometer or thermal actuator design in MATLAB. So I'll teach you on accelerometer in the next class, and we can like check the this sorry, MATLAB results as well. I think otherwise I think I have a file somewhere here. I can show you that as well. Okay, can I run this one? Yeah, so this is one kind of suspension design which I'm showing. This is for accelerometer. So you can play with the design. This is one kind of design. You can play with the design and like analyze of your own. So I have a like code for accelerometer design as well. So yeah, any other questions? So in accelerometer, we'll not not just how it is deforming. So we should be like careful about the bandwidth, sensitivity, and other things, right? If you have a idea on accelerometer, I hope you understood that. So we will be like doing that as well. So how the bandwidth or like sensitivity is changing. So we'll work on that as well. So and come up with a like very best design. Any other questions? Please let me know if you have any questions. Yeah, if you have, it's like 325 Ireland. If you have if you don't have any questions, I'd like to stop here. Thank you very much for your time. You can always like email me. Is there any difference between COMSOL and Coventor? I haven't used Coventor, but people find it very easy. The people in the past, they used to use Coventor as well. But nowadays, like COMSOL has so many options. You can do a lot of things in COMSOL. So I think because of that, people are using COMSOL. Yeah, Coventor. I have seen few people who like design accelerometer in Coventor as well. But I think like COMSOL is a like very handy thing. You can do a lot of things there in COMSOL. So I think because of that, people are using COMSOL. Because in Coventor you can work on some MEMS devices as well only, right? But in COMSOL you can do structural, fluid, and anything, optimization, anything. So I think because of that also, like COMSOL is famous. There are also other FEA software. Some people work on I think ANSYS as well, or Abacus. There is another FEA software which is like Abacus. Most of the people work on structural design on that. So yeah. Any other questions?
Okay, so if you don't have more questions, so I would like to thank Suman for your very interesting and insightful talk and all the demonstrations and simulations and all the information. I'm afraid we need an extra session to complete
Yeah,
this formation about MEMS design and in particular the accelerometer.
yeah,
So we will try to schedule an additional session in between this one and the last one. So let's see the availability of Suman and we
yeah,
will let you know about the next session as soon as possible. So
yeah,
thank you very much for attending the training session today, and thank you, Suman, for all the
yeah.
information.
Thank
Thank you
you.
very much.
Yeah, thank you, Carlos.
Thank you.
Bye.